I am Xeno Kovah. What you need to know about me is that this particular work is work I do with the minority of my time. The majority of my time is spent on open security training to a nonprofit I run where I create free classes and give them away, and I encourage other people to create free classes and give them away. So this is not directly related to free classes that are going to be given away, except that it turns out I created too much material, so I'm probably going to turn this whole thing into a free class and give it away. Alright, so alakazam, boom, these particular Bluetooth dongles can now send arbitrary low-level packets that they're architecturally not supposed to. And there's your magic command, sudo copy, Xeno's magic firmware, over the Realtek firmware, and you've got arbitrary code execution. So today we're going to talk about magic's biggest secrets revealed, or at least that's what I wanted to talk to you about. So what I wanted to present was not just what I found, but how I found it, so that other people could follow in my footsteps and do the same thing for other chips, because there's a lot of chips that need exploration. I made 350 slides, and then I decided that's not going to actually fit in this talk. So I cut it down to a lean 140, and we're going to see what we can get through. Now, the abstract promised you that suffering builds strength. That is one of my life philosophies. You saw some of that yesterday. Marius suffered for his incorrect wiring on his glitching setup. Weiche, he suffered for being able to only use core dump crash logs in order to debug the MediaTek chips. Suffering builds strength. That's 100% true. And so I hope you understand when I tell you that I hope you too will go out and suffer, so that you too can gain the strength to do awesome work. So in this talk, terminology, BC or BTC is going to be Bluetooth Classic, not Bitcoin. BLE is Bluetooth Low Energy, and BDADDR is a Bluetooth device address. It's that thing that looks like a MAC address, but it's not a MAC address. What you need to know about Bluetooth addresses is that spoofing a Bluetooth Classic address or a Bluetooth Low Energy public address is hard. There's no official way to do it. And spoofing random addresses is easy because there's official APIs that you can just use. So, motivation one for this talk. This is why it's sort of OST2 related, but Veronica and I wanted to show machine-in-the-middle attacks using WAD wireless hacking framework in our future open security training Bluetooth Low Energy class. But there's no architectural way, as I just said, to set Bluetooth Classic addresses or BLE public addresses. So WAD will help you machine-in-the-middle a device that's using a random address, but it won't help you machine-in-the-middle a device that's using public. So if you want to attack something using public, you need to have some way to spoof the BDADDR. And there's no good ways to do that, except that some really old chips, like the CSR4 dongle, have some really old deprecated tools, like a tool called BDADDR from Bluesy that just doesn't even come included anymore. Those tools know how to spoof the BDADDRs on those old chips. But the CSR dongle is called the CSR 4.0 for a reason. It only supports Bluetooth Spec 4.0, which is the very, very first one that supported Bluetooth Low Energy, so great. It can do Classic and could do Low Energy, but this is only supporting features from 2010. So we're teaching a new class. We don't want students to be locked into only 2010 stuff. So we need new hardware that we can teach to that speaks to Bluetooth 5.4, which is what we teach in the class. Secondary motivation. I have Bluetooth printing. I presented it here at hardwear.io 2 years ago. And that uses some security researchers tool called Bracktooth. Sorry, I'm going to even though I don't have time for it, I got to give you a big mouse because then you'll see what I'm actually pointing at. There you go. That's going to actually matter later. So Bracktooth, that's what I was using in Bluetooth printing for LMP, sending arbitrary Bluetooth Classic low-level link manager protocol stuff, but the source code's not available. That's not great. It also only supported x86 when I initially started the work, and it uses a big dev board like this, which forced me into using a big x86 board instead of a small little ARM-based single-board computer. And then I had to use voltage adapters to use big old honkin' power supplies and everything. Another problem with using Bracktooth for sending low-level packets is that it requires an ESP rover kit. You literally can't even buy those anymore. I had to go off and find what the replacement is. Those cost $55 and they're big and bulky. And I would rather have people that I teach Bluetooth printing or people actually doing Bluetooth printing, I'd rather have them use a simple USB dongle than a big old dev kit. The third motivation for this is that I'm putting together a blue crew of people who want to do awesome Bluetooth security research. If that's you, get in touch. But basically, I wanted to lead by example for the blue crew, which is to say I wanted to go off, reverse engineer something, say, here's how I did it. Now you go off and reverse engineer Qualcomm or MediaTek or any other thing that hasn't been looked at, because almost everything hasn't been looked at. There's like 3 or 4 chips out of 20 plus chips that have been looked at. We need more people digging into this stuff. So the future the current Bluetooth printing class is there on Open Security Training. Veronica and I are making more classes. Blue Crew members will be expected to know all the stuff about Bluetooth that we put out there, and then they're expected to go off and do cool things. So, time for meat. So what's on the agenda? Suffering and strength, right? So I don't want this to come off as whiny. Hopefully, I'm not whining that, oh, I suffered and it was hard. No, suffering is good here. Suffering builds strength. You got to break yourself down a little bit to build yourself up a little bit better. So the types of things I ran into is that this particular chip was MIPS 16E, and I don't know MIPS. It has no private or public SDKs, has no strings really. There's like 10 strings, but turns out those 10 strings are good enough. No JTAG option, no live debugging, anything like that, and end up having to write code in an unfamiliar language. So started this work back in last January with a plan that someday we needed to have better chips for our Bluetooth classes. So I go off and buy a bunch of dongles on Amazon, just some random cheap stuff. And they say they support 5.3 and 5.4, but when you plug them into Linux, run HCI command config-A, look at the verbose output, it tells you, okay, all of the chips I bought turned out to actually all be Realtek stuff, and you will see this. If you buy random white label, cheapo Bluetooth dongles, it turns out most everything's using Realtek today. So it's using Realtek, but the chips, according to themselves, report they only support Bluetooth 5.1, not 5.3, not 5.4, like the people are putting. And I confirmed this later with Realtek that yes, they only support 5.1. Those sellers are straight up lying. So I didn't know at the time, I hadn't cracked these open at the time, but if you got them, you crack them, and you find out that they're using Realtek 8761BUE or BUV. And actually, I show this picture just to say, I really expected all the white label stuff to just be the same on this inside with like a different plastic shell around it. So I was actually somewhat surprised that we did see different PCBs and different chips. So then, had I actually went off and read the data sheets, but I did that later on, the BUV is a USB interface, the BUE is a USB interface, and turns out there's 2 other chips that have UART interfaces. So what I did that was wrong, which caused me a little suffering, was that around April, when I started to think, okay, maybe I am going to poke at these things at some point in the future, I just Googled RTL8761B dev board, and I went out and got the wrong dev board. I said, okay, there's a USB port, and it's got the Realtek chip, so this must be the dev board for playing with those USB dongles, right? Wrong. So it turns out, like I just said, there's a thing that uses a USB interface and one that uses a UART interface. So this USB is actually only for power. It doesn't actually speak data over the USB. Do as I say, not as I do. Double check your dev boards, specifically the interfaces, because there are different physical transports that Bluetooth uses in order to speak with chips. So the actual start of the project started this last July when I got the Bluetooth printing class up in Open Security Training. I'm running that, and in the background I say, okay, I've got a little free time. I don't have to pay attention super much to the students. They'll post questions whenever they post. So I said, okay, let's start looking at these Realtek chips in the background. Maybe we can use these for the future. And so I plug in the dev board, there's no lights, there's no power, there's no indication this thing actually works. So I messaged the Alibaba sellers a little bit peeved, thinking that they've deceived me and sold me some garbage. But they said, look, we just ship whatever Realtek gives us. Talk to Realtek. And I did. I sent off emails and heard back from them later. But while I was waiting to hear back from Realtek, I go out on my OSINT hunting to find out what I can find about Realtek stuff and how it's used. So, if you look on Linux, you will find that there is a lib firmware RTL-BT and RTL various other stuff, Wi-Fi and so forth, but there's a Realtek Bluetooth folder full of Realtek Bluetooth chip firmwares of some sort. I don't know what these are at this point, but they say they're firmware. They're in a firmware directory, so that's probably some firmware. So furthermore, if you go off and do your OSINT and you do Googling to find out who's ever reverse engineered Realtek stuff, you will find a few hits for Wi-Fi things. You will find 0 hits for Bluetooth things. So, Wei Che yesterday saying, oh, there's only 3 things for MediaTek. I'm telling you, there's 0 things for Bluetooth on Realtek. But 8051 enthusiast that he is, was looking at some Realtek Wi-Fi chips which happen to be using 8051 based processors for their Wi-Fi cores. And while he was looking at that, he happened to just poke at the Bluetooth that was also co-resident on these chips. And what he found was that there seemed to be a bunch of repeating patterns of 006F. He did a little bit of analysis and ultimately concluded he thought that the 6F5 was the no-op instruction. So then he had to correlate that back. What assembly architecture uses 0065 for no-ops? And the answer turned out to be MIP16E. So just that little hint was enough to get me going with those firmwares that I found on Linux. So cool, they're probably MIP16E, which is a short form encoding for MIPS 32-bit instructions in the same way that thumb is a short form encoding for ARM. But oh noes, I don't know MIPS. Do I? Well, luck is what happens when preparation meets opportunity, which is why I tell you all to go out and take all those classes on open security training, get lucky in the future. Well, I got lucky because I teach a class on RISC-V assembly for OST2. It takes you about 28 hours on average, maybe more, maybe less. But the opcodes for MIPS significantly overlaps with RISC-V. Actually, they share similar lineage. MIPS, in some sense, you might call RISC-3 or RISC-2. Like it's just a earlier antecedent of RISC-V. So even if Ghidra's decompiler didn't work, which it did if I use x86, I could still understand the assembly. And so, again, get prepared to get lucky by taking OST2 classes. I got lucky in this case. So even though Ghidra could disassemble these, it didn't really work particularly well. And so you throw it into Ghidra, you select MIPS. I didn't even see this until I was making the slide. It does say MIP16E down there, so that's the right thing to select. And then you find some header information and you find a bunch of zeros. But when eventually you get past the bunch of zeros, you do what you normally do. You select it, you hit D to disassemble, and you get invalid instruction, or at least it doesn't continue on with valid instructions. So the right way to deal with this for all of you future people who are going to run out there and grab a Realtek chip is that you need to hit F12 to disassemble as MIP16E. If you do that, you get a whole bunch of assembly instructions. That looks good. That's great. Hit F, define a function, keep running, and then immediately stop, because immediately after the assembly is a bunch of data references, usually in those small 16-bit encodings of assembly instructions. You can't put a 32-bit reference to a 32-bit memory address, so you got a bunch of data references at the end that are referenced from within the assembly. And basically, Ghidra just doesn't like that, doesn't continue. It should just say, like, code, data, okay, continue. It doesn't. We keep trying, we assemble, and we keep running into problems. So what do? You file a Ghidra issue, and then you play the waiting game, right? No, the waiting game sucks, so let's have Veronica make us a Ghidra script instead. So I asked Veronica to make a script. I've never bothered learning IDA or Ghidra scripting because I have a reverse engineer in my house, a former NSA engineer who may or may not and cannot confirm or deny whether or not she ever used Ghidra before it was public. So ask her to make a script for you and basically, easy mode. Now we've got a whole bunch of assembly for the firmware files, but we still don't know exactly what is contained within the firmware. More assembly, mo better. Woohoo! And do, there's still no strings whatsoever. Okay, well, we're going to keep going. Go back to OSINT, just always, you go up, you go down. This is a very important thing in reverse engineering. Go deep, go up, go broad. Go deep, go up, go broad. So download all the documentation I can find for any Realtek chip. Don't care whether it's my chip, because there's probably architectural similarities between my chip and other chips. So this is a diagram of the Bluetooth stack for both Bluetooth Low Energy and Bluetooth Classic. But what we care about for our purposes is that Linux is a host that can speak both Bluetooth Low Energy and Bluetooth Classic. And this Realtek chip down here at the bottom is a Realtek chip can speak both Bluetooth Low Energy and Bluetooth Classic. So How things normally work with Bluetooth is that you have a Linux host and it sends HCI host controller interface packets across to the host controller interface, things like official commands, set a random address. That's why I said random addresses are easy mode, because anyone can just say set a random address. There's no equivalent for public addresses, which is, as a reminder, what I'm trying to figure out right now. So they can send things like that. They can send things down to classic side saying inquiry, like tell me what Bluetooth classic stuff is out there right now. But you can also have things like a Realtek driver running in the background sending magic vendor-specific commands. So vendor-specific commands are officially spec'd out as having a special number, 3F, for the group, and then whatever the vendor wants for the actual command. In this case, 20 for some sort of vendor download, vendor firmware download type thing. So what I can see by just like plugging in a Realtek dongle and using something like BTMon is that it's sending VSC, OCF, that's opcode command field, OCF, just command 20, 20, 20, 20. It's sending fragments of those firmware files that are sitting on the Linux file system. Also followed by a configuration file that's sitting on the file system. So you can confirm that for yourself. You just run BTMon within Linux, attach a dongle, and you'll see a whole bunch of these vendor-specific commands. So those config files are interesting because they're sitting right next to all the firmware files, and leaked documentation indicates that they do have the capability to set the BDADDR. This is how Realtek allows people to set the BDADDR, except for this particular chip. It's not, the leaked documents have the exact way to configure this, but it doesn't work on this chip. So it turns out like something about the format of the config file is different for this chip than the leaked documents. Got to talk a little bit, like I'm only talking about this to give like the hint that like anyone anywhere that ever wants to do Bluetooth reverse engineering, if you're going to reverse engineer the Bluetooth controller itself, you need to let the specification be your guide. So the format of those HCI commands, the special commands going down from the Realtek driver, when it's using a vendor-specific command, the least significant 16 bits are broken up annoyingly into a 6-bit field and a 10-bit field. So the 6-bit field is the opcode group field, the 10-bit field is the actual command. And so when you're looking at this, the 3F that is mandatory for vendor-specific commands must be shifted up by 10, and therefore if you see any constants like this, then those are kind of going to be your hint when you're reverse engineering. If you see 3F, if you see those constants that are 16-bit, FC, FD, FE, FF, if you see shift by 10, these are the kind of hints to you somewhere in the code there is some vendor-specific command processing going on. So always let the specification be your guide. You need to use the hints that the spec gives you about magic numbers and things that must be in order to do the reverse engineering. So now, finally, 801, we have some instructions from Realtek about how to turn on that dev board that was shipped in a state that cannot actually power on. Here's the jumpers you set, just including that for posterity. They sent it in a confidential document to a person who has no NDA, so there you go. Should have really shipped that way, right? Don't waste my time. All right, anyways, so what do you do when you can power on your board? Well, this particular board, as I said, is the wrong board. It is using the UART interface. So what you have to do is you have to connect up to the UART, plug in like a USB to UART adapter, plug it in, run screen or what have you in order to see the serial output, and you see a whole bunch of nothing. And then you debug it with something like a logic analyzer. And what do you see? You see a whole bunch of nothing. So my dev board is doing all of nothing when I power it on. So, back to OSINT and just running around, fiddling around. But the most useful discovery of this research occurred on 803 when I was looking at tools, a particular tool, RF test tool, which is just a Windows tool for other devices, not for this particular chip, but it did have an interface which requested a COM port, a serial port in Windows parlance. And that particular tool had capabilities like read the BDADDR. So I could see this tool, I actually got it working on this chip, and it can read the BDADDR, that's the true BDADDR. So I know this tool interfaces with this chip fine. What I need to figure out now is how does this tool work? Right? I need to sort of reverse engineer the tool, but I want to do it more dynamic analysis rather than static analysis, if at all humanly possible. The most useful thing being that there was this function rwregbt, and if you pulled up that background command menu bar, you got this new tab appearing. And this new tab had these things like bt-rwreg. Well, we might infer that that means Bluetooth read-write register of some sort. It's got RF registers, modem registers. bt-soc-aon probably stands for system on a chip, always on, domain of power. So there's a thing, we connect it, and we try out some stuff. We try a bunch of different addresses, and we get all zeros. We would call that inconclusive, right? I don't know whether this is actually doing anything useful at this point. I can read, and it seems like it's doing something, but it's sending me zeros. That's not useful. So, Geedra tip of the day is that when you want to find out where you should potentially be reading to an address that might be truly valid, then you go to the defined data, and you scroll through that. And what you're seeing here is that there's a whole bunch of stuff in the range 80 something. And you can actually see over in this assembly at offset 30, like literally the very first assembly, you can see that it'll have in blue addresses which are defined within the context of the blob of data that I've included right now. And there's addresses which are not defined within the context of the blob of data. So I've just allowed this to be located at offset 0. And it's telling you, well, I'm at offset 0. I've only got hex 4000 worth of firmware data, but some sort of access is going on to address 8010, blah, blah, blah. So stuff up in the 80 range seems to be accessed by this firmware. Don't know what it is, but I want to go try to read that instead. So run down to the last defined data. I can see it's accessed from many different places in the assembly code that I've already loaded. Go ahead and do that, throw that into the tool, and boom, we get some non-zero values. That's what I want to see. That's saying something interesting is going on here. And move on to try all the other types, get some non-zero values for that other type as well, but also get this nice little hint here. We've got a quote-unquote read flash, and it is at some sort of FC61. Well, to me, that now looks like a vendor-specific command. I said, be on the lookout for 3F shifted up by 10 bits, and those are what are vendor-specific commands. So this looks like vendor-specific command number 61 to me at this point. Only problem being that this particular chip definitely does not have flash. So it is just running from ROM with some ephemeral RAM and information sent into it. Okay, well, so now I want to figure out, like, what is the tool doing behind the scenes? You're not supposed to understand this diagram. That's just the Windows architectural Bluetooth diagram grabbed from some Microsoft site. But the basic point is I've got some Realtek tool I found, and it sends some sort of magic command down to my chip somehow through the Bluetooth stack and or through the serial stack, lands down here at my serial adapter, sends over to the board via, serial, the HCI data. But to figure out what's really going on there, I'm going to hook up this ALA logic analyzer and just read the same wires that are being sent off to the dev board. And then I can just literally see what's going on with this tool. So send a magic command here. It says it's reading flash. What's going on behind the scenes? Let's look at what kind of data we expect back, what sort of data we put in. So there's your diagram, but thankfully for you, I like to zoom. So we can see in the serial trace that it is indeed sending some sort of data like FC61. So that looks like a vendor-specific command. We can see in the serial trace that it's sending something that looks like the address that I requested to read, 8012 DC50. We can see a 20, which because we know 4 bytes of data come back, that's probably a 32-bit hex 20, 32 bits worth of data to read, and that 5 is probably just the length of this data right here. So that looks like some sort of read from a 32-bit address of 4 bytes of data, and indeed I see the full 4 bytes of data coming back here. So cool. At this point, I think I've got a special magic command. I think it reads, I don't know 100%, does it read from some offset in memory that it thinks is where flash starts? Does it read from the base of memory? I don't know. It turns out the answer is it reads from the base of memory. So you're just giving an address and you get to request anywhere within the 32-bit address space. So what do you do with that? Well, you just try to scan all of memory, right? And you don't want to scan every single byte of memory. Instead, you want to do hopping and scan little pieces of memory. If it's invalid, this chip's memory controller seems to send back dead beef. So what you do is, just in case it's using paging, unlikely, but just in case, you do hex 1000 chunks of memory, you skip forward hex 1000, just read 4 bytes and see, did you get dead beef or did you get anything other than dead beef? And what you come up with from that is you get some sort of memory map. So cool, I now have a sense of like what the ranges are, and the ranges make sense according to my assembly, which was reaching out and trying to grab stuff in the hex 80 something range. That's the final thing, can't dwell on it, don't have time, rocking through these 140 slides, but there is some aliasing going on in there as well. So, now at this point, I have scanned all of the memory, I've figured out the memory map. Now I can read all of the memory that is within those valid memory ranges. So I've got what I think is probably the ROM at 80000. So I load the ROM into Ghidra along with all the existing firmware so that now the existing firmware can reach out and grab data from the thing that I think is the ROM at hex 8000, hex 80s. But there's still no strings. But thankfully I'm an optimist, and so I go ahead and I use the Ghidra manual search for strings. You get all the normal sort of garbage that you would expect, and out of all the strings in the entire thing, everything is garbage except for like exactly 10 strings. But those 10 strings are super, super useful because, for instance, it's saying something about HCI commands, HCI events, LMP, which is the packet data type that I want to send later on. So cool, that is super relevant to my interests. What do you do when you have a useful string? You go check the cross-references. Where is that string used? What code uses the string HCI? Check the cross-references, go there, and it's finally decompilation time. The first and essentially only use of these strings, there's 2 aliased copies of this function. The only use of these strings is essentially a single function gets called over and over. It gets called with those strings as one of the parameters. It gets called with another parameter that is unique to each thing, so we might think there's maybe some sort of registration going on where it's saying like, this thing gets registered as index 3, this thing gets indexed as register 7. And again, it's got all sorts of different data for other parameters. So what do? Said, I'm looking for vendor-specific commands, how these sort of things work on this system. So HCI command probably is where I'm going to find vendor-specific commands. Go look at the data. The data itself points here. Well, that data further points to some particular function, so you have to go skimming along through the function. Now, for the interest of time, I can't show you the nice animated version. So suffice to say that if I just skim down through that function, which is pointed to by the single function registration that includes the string HCI command, there's going to be a bunch of references to data where it says, this variable, is it equal to 3? Is it not equal to 4? Is it equal to 8? Is it not equal to 6? And is it equal to 3F? And 3F is when your eyes light up and you say, 3F, that's the special magic vendor-specific opcode group field. And indeed, if you let the specification be your guide, you will see that all the other opcode group fields for all the other HCI commands are in the range of 1 through 6 and 8. So all of these numbers that are checking it, all sanity checks out. 3, 4, 8, 6. These are numbers for opcode group fields. These are numbers for HCI commands. And so this thing right here really looks like if it's using an opcode group 3F, then call this function. So that seems like that's probably the process all the vendor-specific commands function. Drill down into that. Again, don't have time to show you the nice form, so the quick form is, yes, there's totally a bunch of those special magic range values of FC something, FD something. We even got this FC20. That FC, we said vendor-specific command 20 was the like firmware download thing, so I can drill into that specific function if I want and really reverse engineer how the firmware download works. But I don't care about that because, hold up, what am I even trying to do here, right? Does anyone remember? Sorry, I don't take questions. So what am I trying to do? I'm trying to spoof the BDADDR, right? So in reverse engineering, you sometimes have to stop yourself from getting lost in the weeds. You go deep, but sometimes just stop, come up a level and say, what am I even doing again? Like, don't reverse engineer all of this. Great. I've got ROM dumping. I've got RAM dumping. I've got the capability to go read a bunch of code. How about I don't? Instead, what are my goals? I want to spoof the BDADDR. Now I know a little bit about how config files are being used, how vendor-specific commands are being used. I could drill into vendor-specific command 20, but instead I go off of Google in again, and I go to GitHub and I search for things, and what I find is there is some utilization of the configuration files. There's a function called getMacOffset, so even the vendors call BDADDRs MAC addresses sometimes. GetMacOffset for this particular chip, 8761B, is hex 30. So now I can put that together with the leaked information about config files and get my magic commands. So basically some sort of special header, some sort of total size length, that's 9 for the rest of the bytes. 30 is the offset where essentially this config file is saying, go to the beginning of some sort of config stuff in memory, go to offset 30, plug in a BDADDR, and that's what we'll use for our custom BDADDR. Otherwise, they use one that's burned into OTP. So cool, I've got that. I just write it in a literal text file. I reverse that text file to a binary file. I compress that binary file. I move the other file out of the way. I copy it over to where it's supposed to go. And boom, I've got a custom BDADDR. Goal 1 achieved. Hold your applause, please. We have to keep going. On to goal 2. So, cool. We can now spoof BDADDRs. We can say anyone who wants to use WAD to go off and do machine-in-the-middle attacks against devices that happen to be using public addresses, feel free to. Now you know from those previous slides how to configure the few bytes in order to spoof your BDADDR. So, the stretch goal here was for Bluetooth printing purposes. I wanted to get rid of those bracktooth big dev boards and move down to just a custom little Bluetooth chip on a normal USB dongle. So there's 2 ways I could go about that. I already showed that I have the ability to go reverse engineer all the vendor-specific commands, but I also have memory read and memory write capability. So which is the better way? As I said, if you cannot have to read all the code, that would be the better way. So I need to make some sort of tool. My tool needs to speak over HCI. It needs to send my packet data of what I want to send later on. And then it needs to reach somehow to the LMP layer, the Link Manager Protocol, Bluetooth Classic lowest layer, always baked into the chip. And then that should send off that packet data for me. That's the goal here. Cool. Backing up a step, just want to say, I hopefully didn't miss the obvious. When we look at the, leaked documentation for the RTL, 8761B, if we look at the block diagrams, there is no even JTAG or debug or any sort of thing on the block diagram. And they could just be leaving it off the block diagram, but I don't think they are, because if you look at it for other chips, they put it on the diagram. So some other chip, ARM-based chip, has SWD. So how are they debugging? I don't know. I suspect via serial debug, basically like printf debugging. I don't know. But also we can see if we look at the pinout for the particular chip, there are, again, no easy, obvious, there's the SWD, there's the TDIO, there's no obvious pins that are labeled according to debug interfaces. So I'm not probably going to be able to get a hardware debug access. So instead I need to figure out how their whole patching firmware update mechanism works. And I'll tell you that there's just generally 2 ways that people tend to do this. In a ecosystem like Bluetooth, where the majority of the code down at the controller level, it's just baked into the ROM. So you can either have everything's in the ROM or maybe it's booting off flash. But it's very common for it to all be in the ROM. And so the problem is if you need to patch the ROM somehow, because you have, they're gonna have bugs, you need to patch the ROM somehow, there's basically 2 approaches. The first is they have something like patch registers, patch RAM. These are sort of architectural things baked into the design of the chip, where you can essentially say there's a big row of registers that you put addresses into, and as the CPU is executing code and the program counter is going through addresses, the hardware says, oh, program counter equals that value from that register. I need to redirect somewhere else and run some other code. So that's sort of patch register, patch RAM. Maybe the other place is the patch RAM. The other way you can do it is that you can sprinkle little, if this function pointer is not equal to null, call the function pointer. Sprinkle that through your ROM, and then update RAM locations which are otherwise equal to 0. So set if function pointer in RAM not equal to 0, then call the function pointer. If not, keep going. So I'll tell you straight up, it's using the if function pointer not equal to null version. The reason I can say this, I didn't know this going in a priori, and I didn't really initially care super much, but it became obvious eventually through just looking at enough code. You can see that we have here things where it says if code pointer, this particular address not equal to code pointer 0, then go down here and double dereference this code pointer and call it with a bunch of parameters. And so that's just a roundabout way of saying if the pointer's not null, call it as a function pointer. So that's what it's doing. If we went off and looked at this particular address, 80009, whatever, that particular address has another particular address. That's why it's a double pointer. and that particular address holds zeros by default anyways. And so you can think of it like how the patching mechanism really works is that they load some stuff into RAM, the ROM jumps to that stuff goes and fills in a bunch of function pointers anywhere that they want to sort of hook the existing code execution and control flow. So literally it's architected for dump some code on and hook the control flow. Obviously I can use that to dump some code on and hook the control flow. Just a matter of figuring out how. Alright, not bad. So, the suffering truly begins 5 days from the CFP deadline. So, I have to back up for 2 seconds to say that on the 18th, we come back here to the 7th. I told some security researchers on a Bluetooth private Slack that, hey, we can figure out the spoofing the BDADDR. People don't need to use the CSR4 dongles anymore. Then Antonio Vasquez Blanco, who's a Bluetooth security researcher, on the 15th, he provided me my memory dump script in his Scapy USB Bluetooth library. So he had made a library that talks USB, Bluetooth, and then uses Scapy for packet crafting. So he just said, hey, if you use this, you can talk to a normal USB dongle instead of your serial thing that you were using. And so I thanked him for that. I used it, and then on the 18th is where the story picks up. Then I went and analyzed Bumble. Bumble is some Google open source code for doing Bluetooth, and Bumble already had support for doing patch download onto Realtek chips. They already had grabbed the algorithm from the Linux code, which is open source, and they had implemented it themselves. So then I grabbed it from their code and implemented myself in the Scapy USB Bluetooth. So the initial POC, basically it downloads my code into memory. It takes the initial patches, puts them into memory with a little prologue hook at the very, very first function. And so the idea is when the very first function is called, it will jump down to my POC code and it will jump back up and continue execution in the normal code. And for what it's worth, this is how I was programming assembly at this point. I went and I looked at the assembly language. I would grab something like, hey, I need an OR assembly instruction. I'd grab that and then I would fiddle with those bits until I changed, value 1 to value 2, register 1 to register 2. So this is how I was writing MIP16E assembly at this point. I didn't even open the manual yet. I was just take that, fiddle with the bits. Great, good, keep going. Got 5 days to go. But POC 1 doesn't work after 4 hours, suffering, debugging. And eventually I decide, okay, well, I wrote my code into some memory that I hope and I think is not being used, but that's not particularly safe. So instead, let's tack my code on the end of the original patches. Same idea. And let's feed that in. Again, another 4 hours. No go, but finally, 14 and a half hours into the day at 9 p.m., I figure out there's a double D reference. That should only be a single D reference, right? Writing assembly in some unfamiliar language, doing it wrong, suffering, but becoming more strong for that. So finally, POC 2 is working at the end of the day. Time to hold up. We've only got 4 days to go. What are we going to do? How are we going to get arbitrary LMP packet going? So it's time to break out the big guns. This is my brain food. Your brain runs on glucose. When you need to get anything done, you give it a boost. Little bit of sucrose like so. So cool. Now, I've got 4 days to the deadline. I want to send LMP packets. The thing about LMP packets is they have to be sent in the context of an active connection. It's not just like an advertising packet. I don't know about Wi-Fi from yesterday, but those management frames, I feel like management frames just get sent around without an active connection. We need to create and establish a legitimate active connection. Then we can send LMP packets. That's where we're trying to get here. And so Scapy USB Bluetooth is really not meant for that. It's really not particularly good at create an active connection. Now I've got a raw socket, but then I have to manage all the state myself. Antonio helps me out. He at least gets me to the point where I can create a connection, send an LMP name request using normal legitimate HCI, not my custom crafted packets. And then I go off and I try scraping through memory on the recipient Realtek dongle. So now I've got Realtek sender, Realtek recipient. I can scrape the memory on the Realtek recipient, but I can't find my packets anywhere in memory. I just straight up scrape memory. It's not there. And so then I waste the rest of the day reverse engineering LMP more because I've been spending more time on HCI than LMP. Cool, 3 days to go. And, 4 minutes to go. So basically, at that point, It's worth saying that, like, Bluetooth Classic, there's no good ways to sniff the packets, and so I have to come up with my own way to sniff the packet, which is my 2 dongles, one of which now turns into a logging thing, because I don't trust that I'm sending packets unless I can see it, quote-unquote, over the air. Well, second best option is see it on the recipient that it received the actual packet. So, around this time, for what it's worth, had a little conversation with Veronica where I said, hey, I need to write a lot of code now. It's time to start breaking out the MIP16 assembler. And she said, you were writing your code in hex? That's the dumbest thing I've ever heard. And I said, thanks, honey. That's going in the slides. All right. So basically, suffering. I'm not going to dwell on the particular suffering again. I don't want this to come off as whiny, but the point is everywhere you see suffering, you are also seeing me leveling up in terms of my MIP skills and my writing assembly in a weird environment where I have to use like memory dumping for debugging. Like, I don't want to say like, yesterday, Weiche, he had like core dumps so he could see register values. I didn't have register values. I have memory dumps. I have to put in assembly to get register values. Whatever. Level up. I now have patched code inside of the Bluetooth controller. I can use legitimate things like remote name requests. So basically when you get a name request from a remote thing, it's supposed to take a buffer of like 253 bytes and send it up to the host. I'm using that now as my LMP logging mechanism. But at this point, my primary fuel is exhausted. This is 2 days later, by the way, that I made my way through that. And it's time to switch to auxiliary boosters because we got, one more day to go. Suffering. And finally, a critical decision point, 3.5 hours from the CFP deadline. Do I keep coding up until the CFP deadline and confirm that this all works? Or do I actually write up my CFP deadline? Which do you think I did? Well, at this point I was zen because I knew that this could work. I have this arbitrary write capability, arbitrary read capability. I am super confident that I'm going to get arbitrary packet sending capability. It's just going to be slow and hella painful. So my power reserves are spent, and it's time to now go on intermission and go off and do all the other stuff I've been putting off. But I put in my CFP submission. As you may or may not know, sometimes speakers don't actually have their full stuff working before they submit a talk. Pro tip right there. Anyways, later on, come back, spin up, figure out that it doesn't like the various hackish ways that I'm logging information. That's breaking connections. Switch to other stuff. Switch to Bumble. Bumble is using object-oriented programming. That's my kryptonite. I can't handle abstraction layers. And so I say, okay, Veronica, you're going to read the code instead of me. She's got a programmer mindset, but then I have to create a special lab setup for her to actually test my code and read the Bumble code. That takes 2 days to set up. I give it to her, and then an hour and a half after I give it to her, I figure it out, quote unquote, myself using GitHub Copilot and ChatGPT. I finally figure out how to get Bumble to send my vendor specific commands. And the final progress is on the 23rd, I can now send an LMP packet using a function that I see in the code to send that exact packet. And then one little bit more of suffering is that I finally figure out how to send the actual arbitrary LMP packet, which has 6 arguments, and you can only send 4 as registers, so I have to learn about their calling conventions and everything else. And finally, boom, goal 2. I've completed sorry, don't clap. No. And so basically CFP deadline plus 2 days, 2 work days, I've actually now got this arbitrary capability to send a blob of data down and get it sent out over the air. So I can get rid of Bracktooth. This is not even the final form. The dark firmware Real, which is what we're going to call this, it takes a bunch more suffering to get it working with Bluetooth printing. Not going to care about that point. But the nice takeaway from that is that forced me to turn it into the standalone file, which gives you the magic commands where you just get to now overwrite a file. Instead of doing dynamic download, just take a file, stick it on the file system, and you get to put the custom firmware onto the Realtek chips. And alakazam, these things are now able to send stuff they're not supposed to. So, taking a step back, I'm going to leave this for future Bluetooth researchers to read. To do better work in the Bluetooth space, we need people not just saying there exists a vendor-specific command, you need to actually document the parameters of the command. For this particular audience, I'll say it would be super cool if anyone else wants to go off and try to do the exact same thing in terms of ROM recovery using your particular techniques like fault injection or optical analysis, and then contribute that to open security training. We can have students do it the Xeno way and the U way. But yeah, the final one last thing here is that it turned out that Realtek was really nice, and this was suspicious to me. So essentially, I got them to give me the hardware setup configuration. They asked me what I was up to. I told them Bluetooth printing. I thought they were going to stop talking to me at that point. And instead, they turned around and said, hey, if this is what you're trying to do, we could make you an official way to send an arbitrary packet of LMP and LLCP. I said, like, hells yes, I'll take it. So they told me they're not going to do it for the RTL 8761B, but rather the C, the upcoming chip, the chip that they want the other people to move to. They sent me a dev board. I ran their magic commands with their custom firmware. So they literally have this firmware written here in time for hardwear.io. And so it's documented. I got them to take the Realtek proprietary off of that and just say Realtek copyright. So, like, officially, they're going to have a documented way for you to send arbitrary commands. You don't have to rely on my hackish firmware. That is a best case outcome scenario here. I'm not going to do a great job of maintaining it. So the future looks bright. We're essentially having a vendor stepping up and saying, we will give you the capabilities you need to send arbitrary packets for doing fuzzing, for doing vulnerability hunting, and I hope other people follow their lead. That's it. The code is already open source and released. The code, the Ghidra files, everything is released. And thanks to Veronica for making Ghidra scripts. Thanks to Antonio for helping me with an updated memory dump. So I don't have any further time to take questions. I'm going to watch the next talk, so don't come up to me and ask me questions. You can find me over in the coffee area after the next talk, at the coffee break. Thank you for your time.
Wow. That was a sprint. Despite Xeno saying that he doesn't take questions, maybe we can ask one? Does anybody have a question?
What do you got? Come at me. Stump the chump.
Anyone who was capable to following that? All right, we've got one.
So when you were trying to execute your own instruction from RAM, I noticed that one of the last slides you added an epilogue at the bottom, so you were jumping from the end of RAM. What was the reason for that?
Yeah, so unfortunately, like, I had to cut so many slides that I can't tell you, but he did correctly notice that my previous thing said I was hooking function prologues, and eventually it said hooking function epilogue. The answer turned out to be that the existing patch code would insert its patches, and so earlier when I hooked function prologues and I put my patches in, it would stomp my patches, so I need to, like, wait for them to put their patches, and then I stomp their patches instead of them stomping my patches, but still I obviously have to call through to their original function pointer to make sure everything still works. Yep.
Thank you so much. Let's give a round of applause to the person who managed to follow the entire talk of Xeno.